Thank you so much. I appreciate all of you coming this late in the day and last talk of the week. We're almost there. I promise not to make it too painful, although I can't promise. Actually, I can't promise that. But last time we talked a bit about 3D n equals 4 quantum field theories. In particular, we took those 3D n equals 4 theories that I sketched very briefly and reduced them down to one dimension to these 1D n equals 4 quantum mechanical theories that we talked about in the first two lectures. In doing this reduction, we ended up landing on an effective target space. This is like that Kähler manifold I talked about before. And the effective target space in this context was some version of the vortex moduli spaces that we've been seeing in the other lectures. In particular, we have a moduli space of connection and then two sections of an associated bundle. In our 3D theory, we had a gauge group G, some compact Lie group. We had hypermultiplets that were valued in a representation R that took the form of a unitary representation, not cal R, and its conjugate R dual. And so X and Y are my sections of an associated R and R dual bundle. The equations that sort of cut out the low energy solutions say that X and Y are covariantly holomorphic. They satisfy a complex moment map constraint. And there was a real moment map type constraint where this is, of course, the curvature in the plane transverse to this 1D timeline. And this is the real moment map. Of course, this is all modulo gauge transformations. And from this one-dimensional perspective, the gauge group looks roughly like gauge transformations on the complex plane. So it's something like maps from C into our compact group G. And of course, this sort of looks like, or it is, a symplectic reduction where we have this real moment map. So we have this double slash now instead of just a single slash. And by some Kobayashi-Hitchin correspondence, we can throw away one of these slashes so long as we put a subscript C on our gauge group. Today, I wanted to take this perspective and illustrate how we can extract from this effective 1D theory a category of extended operators in our three-dimensional theory. So before I get into that, I wanted to first explain how to get a category out of a topological field theory. So that's going to be the first thing for today. We're going to talk about line operators in a TQFT. Okay, so the basic statement is that these line operators are going to form some category. If you've seen something like Chern-Simons theory, you might be familiar with the notion of like a Wilson line. The same sorts of objects happen in other quantum field theories, and in topological quantum field theories, these operators, as we'll now see, form a category. Before we get to line operators, I want to first mention local operators, which means operators that sort of are localized at individual points in space. So I imagine I have two objects I can insert at different points in space-time, and I can imagine taking a limit where the points I insert them come close together to one another. Because this is a topological quantum field theory, nothing really cares about distances. There's no dependence on a metric or anything like that. And so we would expect that in the limit that these two local operators come close to one another, the limit is non-singular, and we get a new local operator at this insertion point that is a product of the two. So a collision of local operators is going to induce some kind of product structure. And in particular, local operators will form an algebra, the algebra of local operators. In greater than one dimension, we can imagine having our two local operators and exchanging their positions and then doing the collision. So step one will be in white, and then step two will be this yellow. And this will give the other direction or the other ordering of this product. And in particular, we expect to get some commutative algebra out. Of course, we can't do this in one dimension. And in one dimension, you actually would find an associative algebra. But in greater than one dimension, you'll get some sort of commutative or graded commutative algebra. Okay, great. But what happens when we allow observables that aren't localized at individual points in space, but have some extent in, for example, one dimension? So this is what I would call a line operator. I'll call it like L or something like that. So you imagine that along some fixed one-dimensional manifold in space-time, you can insert some kind of observable. And these will be the objects of the category that we're going to try to build later. So a category has objects. In addition to the objects, I need to tell you what the morphisms between these objects are. And the morphisms between two line operators, L and L prime, are going to be the local operators that I can insert at a junction between the two of them. And I can imagine if I had three line operators, L, L prime, and L prime prime, I could have local operators sitting at their junctions. And these will be two morphisms in my category. One morphism that goes from L to L prime, another morphism that goes from L prime to L prime prime. And just as in the local operator setting, I can imagine taking a limit where these two junctions collide. And of course, this will be how we'll define the composition of morphisms in our category of line operators. So in this way, we can imagine colliding these junctions, and this should give us some composition rule on the space of local operators, which would realize the composition of morphisms in our category. And this story continues to higher dimensional operators. You can imagine having a surface, and you can imagine having lines that separate two surfaces and several of those lines, and you can imagine colliding those lines themselves. And in general, you can have n-dimensional defects in a d-dimensional space, and the collection of all n-dimensional objects that you can insert together with the various codimension operators that can join them and join the junctions and so on, this will actually form an n category. But I'm not going to go into all of that. I'll just suffice at one categories. Next week, Justin will tell us a bit about two categories. But I'm going to be somewhat pedestrian. Okay, so the next task is to extract a category from those vortex equations that we've been seeing all over the place. And the first thing I want to do in that direction is actually to do a another reformulation of these vortex equations that we've been seeing. In particular, I want to do a sort of holomorphic version of this statement. What I mean by that is I'm going to choose a holomorphic frame. By that, I mean I'll use the complex gauge transformations, GC, to set AZ bar equals 0, just to make my moduli space a little bit easier, so that the first two equations just say that X and Y are honestly holomorphic. And when we do this, that data can be then translated into the data of a holomorphic GC bundle on C with holomorphic sections X and Y of an associated R plus R dual bundle that satisfy this complex moment map constraint. And we also need to reduce the gauge transformations to those that preserve this holomorphic frame. So we're going to quotient by G, C, and I'll put a superscript hol to indicate that it's a holomorphic gauge transformation that I'm now imposing equivalence under. And one thing I should say, we've seen lots of discussions on the types of surfaces we can consider. I'm mostly going to work on the complex plane C, but you can change this to sigma, a general Riemann surface. But I'm going to work just on C. And in order to do that, I actually need to impose some kind of boundary conditions at infinity, much like the ones that Martin had, that effectively compactify it to a complex projective space. And the most common type of boundary condition I'm going to consider, although you can relax this pretty dramatically, are something called a massive vacuum boundary condition. And these are going to be labeled by the parameter I'm going to call nu, which will be the massive vacuum. So I need to tell you what a massive vacuum is. And then from that, I'll tell you what a massive boundary condition is, or a boundary condition associated to a massive vacuum. So nu is going to be some element in this cotangent bundle to R. So it's some constant X and Y that I choose. And it needs to satisfy the complex moment map constraint. So if I plug nu into my complex moment map, it betters P0. We also need some sort of stability condition. In particular, we need to have nu be stable for some choice of stability parameter on the hyperkähler quotient we saw last time, which was the Higgs branch. We could impose this stability by turning on those real Fi parameters I mentioned. In addition to the stability, I also want to require that the GC action on nu has no stabilizer. So the orbit just looks like GC. So nu has trivial stabilizer. And finally, it's an isolated fixed point for the action of the torus of our Higgs branch flavor symmetry. And let me just remind you, I wrote this in green up here. The gauge group fits into an exact sequence of this form. We have unitary rotations of our representation R. G is some subgroup of that, sort of by definition. R is a unitary representation of G. And the Higgs branch flavor symmetry was the quotient of transformations, unitary transformations of R that are sort of independent of G. And I need this point nu to be a fixed point with respect to the torus, or some preferred torus of that Higgs branch flavor symmetry. And this massive vacuum boundary condition will say that our sections X and Y go to nu at infinity on the complex plane. Okay. So that's great. With this in mind, now we can start trying to build local line operators in this one-dimensional theory that I've been writing down. And these boundary conditions will come up in a little bit in defining an action, or sorry, a representation of this category I hope to build. Of course, if I have a local or a line operator, I'm going to put it somewhere on the complex plane, and it's going to be at 0 for me. So it won't really see this vacuum boundary condition, but this vacuum boundary condition will show up once we come up with a representation of this category of boundary condition. So with that, now we need to ask, what are line operators? In this theory. And there's two complementary perspectives. The first one is we can couple our three-dimensional theory to an auxiliary one-dimensional theory sitting on this line that we have here. And in principle, we could couple to anything. But if we want to have something compatible with our topological twist and with as much control as possible, we actually want to couple to a 1D n equals 4 quantum mechanics. It's in the same flavor as the ones that we've talked about before. The second perspective that we'll see is that we could instead require some singular profiles to our fields, singular. At the line operator, or at the location of the line. Oh, do not cross. So I'll go back over here. I'm mostly going to focus on the first perspective, although it'll be pretty clear that the second perspective is going to also be quite natural. And the first thing I want to describe is what this might look like when there is no gauge group. So in the case where I just have hypermultiplets. So G is just going to be 1, the trivial group. Our moduli space, at least close to the location of the line operator we're going to put, is just 2 holomorphic functions on the complex plane. And we can imagine coupling this to one-dimensional n equals 4 theory. And one simple example is I could imagine coupling to one of these Kähler quantum mechanics I talked about, where the target of my Kähler manifold is just C by itself. And there's lots of ways of doing this, but one example is where I take the superpotential I wrote last time. For the hypermultiplets all by themselves, it looked something like x del z bar, sorry, y del z bar x. And the type of coupling I'm going to introduce is going to be of the following form. Q will be the 1D field I'm introducing. So Q is just some complex valued map from the real line.
But you have, so these x and y's, they are, if you like, vectors, right? With components which you say are holomorphic, right?
Yeah, I'm just using.
But then if they have a fixed value at infinity, what could they be?
Right now, I'm just looking at the local behavior in the neighborhood of the line. So in principle, you would want to impose.
But you are imposing the boundary conditions or not?
I mean, so the boundary conditions are happening at infinity.
And this is holomorphic only in the behavior, in the neighborhood of the line. Is that what you're saying?
I'm about to explain what's happening in the neighborhood of the line.
Sorry, okay.
So the superpotential coupling happens at a single point in the line or on the complex plane. So I throw in a delta function at z equals 0. And then the critical points of the superpotential say that del z bar x equals 0. So x is indeed holomorphic. This just comes by varying this with respect to y. So this is like del w del y equals 0. If we vary with respect to x, we see that del z bar y minus q times a delta function is 0. So y will not be holomorphic. It'll be meromorphic. And additionally, if I vary with respect to q, I then see that x times a delta function at z equals 0 has to vanish. In particular, we see that y has the following behavior. It looks like q over z plus something that's holomorphic. So it's got a simple pole with coefficient given by the field q. This is not fixed. Q is just some arbitrary parameter. And x is z times something that's holomorphic. So y has a simple pole and x has a simple 0 at the location of the line operator. More generally, I can imagine having a superpotential where I couple to multiple fields. For example, I could have qx plus q1x plus q2 del z bar x plus ... q to the n del z bar to the n minus 1x. And what this will do is it'll force x to be z to the n times something that's holomorphic. And y will have a simple pole, an n order pole. n. There's a number here that I'm going to be lazy about. So we see that coupling to these quantum mechanical fields Q, we can take our originally holomorphic fields X and Y and give them some interesting pole and zero structure. Importantly, when X gets a 0, Y gets a pole of the same order. I could have also had Y's in here and then given X a pole, allowed X to have a pole and forced Y to have some zeros, and they sort of trade off with one another. Geometrically, the way you should think about this is that I've chosen some kind of Lagrangian in the space of holomorphic maps. And the symplectic form looks like taking a residue of my fields X and Y. Oh yeah, it should have a Z. Yes, thank you. Thank you, thank you, thank you. Now I want to consider sort of the other extreme. Where I have pure gauge theory. So in this case, R and R dual are just the zero vector space. And I can imagine coupling my quantum mechanicals or coupling my gauge fields to a quantum mechanical system that has a G symmetry. For example, I could yeah, I guess I've just been calling them functions. So if I was calling them functions, then yeah, but I haven't really talked about twisting homomorphisms at all. I mean, no, I want the, oh yeah. I mean, I'm pretty sure I copied it down from our paper, right? Okay, take that with a grain of salt. I've got two competing experts and myself, so. Yeah. The classic off by one error. Yeah. Yeah. I agree. Okay, so one example of a Kähler target we could imagine coupling to is a flag manifold of the form G mod P for P a parabolic subgroup. And we can always use the holomorphic gauge transformations to fix this to a single point. But of course, this will break some of the gauge symmetry. In particular, this will break GC holomorphic to the G in this group such that G of 0 belongs to P. Indeed, the stabilizer of a point in here is just P. And so we find that this group of holomorphic transformations localizes to, or gets broken down to the subgroup that lands in our preferred parabolic at z equals 0. Yet more generally, I could imagine coupling to something that's a bit larger than that. I could choose a group I'll call G0 holomorphic. These will be the gauge transformations that aren't broken. So I could choose this subgroup, GC hole, and imagine coupling my system to the homogeneous space G hole C mod G0 hole. And we probably want some finite codimension statement. So this shouldn't be just some arbitrary subgroup. It's got some finite codimension so that this is actually some finite dimensional quotient space. And doing this, we can always gauge fix to a preferred point. And we see that the holomorphic gauge transformations get broken to our group G0. And of course, we can put this together. We can imagine having our matter fields lie in some Lagrangian, I'll call L0, inside our original space of maps, our space of holomorphic maps. I'll just lazily denote that bracket X and Y. And our gauge group gets broken to some preferred group G0 hole. And if this is to make any sense, I need L0 to be preserved by G0. In particular, I expect to have a large class of line operators that are determined by this data of a Lagrangian in this holomorphic loop space and a subgroup of holomorphic gauge transformations that preserves that Lagrangian. And there's a notion of equivalence of these guys that I won't get to talk to you about, but if you're interested, I can tell you afterwards. But the basic idea is that I can perform general meromorphic gauge transformations to relate the data of G and L, or G0 and L0 to one another. But okay. As I mentioned last time, I don't like doing analysis. So I'm gonna take all of this holomorphic things and drop holomorphic and instead talk about algebraic things. And just a little bit of notation. I'm going to denote by calligraphic O the ring of Taylor series in my coordinate Z. And its field of fractions, I'll denote K, which is the ring of, sorry, the field of Laurent series. In which case, the holomorphic loop space looks something like R circle bracket Z plus R dual bracket bracket Z, which I'll call R sub K and R dual sub K. You should think of these as like Laurent series valued entries of R and R dual. And the holomorphic loop group I guess I should really call this a meromorphic loop space because I'm allowed to have poles. And perhaps I should call this a meromorphic loop group. G, circle bracket Z, which I'm going to call G sub K. Oh, yeah, that's fair. If you insist. Okay, so this, of course, is identified with the cotangent bundle of RK. So this data of L0, maybe I should call it whole, and G0 is just a choice of some Lagrangian and T star RK. With that symplectic form I wrote over there. And a choice of G0, which is a subgroup of G sub O, which is where I have only Taylor series entries rather than general Laurent series. And this is some nice finite codimension thing inside of G0. And it's going to be some subgroup of GK. Okay, so I imagine, or I expect to have a large class of line operators given by this data of a choice of that Lagrangian and a choice of that gauge group, unbroken gauge group. And now I get to tell you what this massive vacuum boundary condition looks like. Be new. All this says is that I need to require these holomorphic sections X and Y to belong to the GK orbit of my element nu. So what this says is that they approach nu, at least up to gauge transformations, away from z equals 0. So with this algebraic formulation, I would say that the moduli space, this target that we've been talking about, which depends on my choice of boundary condition B, the Lagrangian L, and the group G, as some intersection of L0 and this orbit of GK, and quotient by the unbroken gauge transformations G0. So this should be some holomorphic or algebraic avatar of the moduli space of vortices on the disk with this boundary condition at infinity, where I require my fields land on this massive vacuum. Correspondingly, based on the general nonsense we talked about in the first 2 lectures, I expect to have a Hilbert space of my 3-dimensional theory in the presence of this line operator piercing through the origin and massive vacuum boundary condition at infinity. to be some suitably defined homology of this moduli space. So this should be some algebraic avatar of the quantized space of vortices that we've been seeing, at least for the zero energy states.
Are you referring to, or you're not referring to anyone specifically?
I mean, it's a little bit subtle, but perhaps the right thing to say is probably some form of equivariant intersection cohomology. Like really, these spaces are like not smooth, far from it often. So in reality, what you often end up doing is pulling this quotient and really doing some sort of equivariant cohomology. And even then you might have some complaints about like L2 versus not L2. So I'm gonna be pretty fast and loose about this. But more pragmatically, we often use Borel-Moore homology. Yeah. Yeah. Okay, great. So this should be some version of the Hilbert space of our 3D theory on a disk or on the complex plane with some vacuum boundary condition. Of course, I haven't really given you much in terms of the category of line operators. I've given you some objects, but now I need to tell you how to derive some morphisms between two objects. So this is a problem that I attacked with Tudor and Justin a couple years ago. And the basic idea is that we're going to use these Hilbert spaces, as I mentioned in the first lecture, to provide a representation of this category of line operators that I hope to describe. So the basic idea that we're going to have, we have our theory with the boundary condition be nu at infinity. Through the center, we have some pair of line operators. Maybe I've already used my calligraphic L, so I'll use a regular L now. I've got two of them, L and L prime, that are each specified by this kind of data of a group G0 and a Lagrangian L0. And the way we're going to describe the morphism spaces, i.e. the type of operators that I can insert at a junction, by doing a state operator correspondence. So roughly speaking, I'm going to imagine I have one disk down here that intersects the line L and the boundary condition at infinity. The Hilbert space of states is going to look something like this homology. And then I'm going to have another disk above it. Again, this one's intersected by L prime. And I'm going to imagine the moduli space on a configuration of this form where I have some set of fields down here and some set of fields up here. And I'm going to imagine all of the possible ways to go from this one to this one that are localized at this point z equals 0. As I mentioned, we can't just take all linear operators that go from this Hilbert space to the next one. We have to have some suitable subset that are localized at z equals 0. So we're going to consider another moduli space that I'm going to call MRav, short for raviolo. And I'll explain why it's a raviolo in a second. But it'll depend on the data of B new, as well as the data that defines the line operators L and L prime. And what does it look like? Well, it'll look like the moduli space above. Or at least the points in this moduli space above. Union over some moduli space on a disk in the middle that contains this point that we've removed for our line up or for our local operator. So this space is like the yellow. This thing in the middle is going to be the green. And in this algebraic formulation, it'll look like a double quotient of our sections X and Y above, together with a gauge transformation away from z equals 0 that can relate the two sections to the sections on the lower disk, such that X prime, Y prime is G X, Y. And I need to quotient by the gauge transformations on both the top and bottom disks. So this will be something like the moduli space of vortices on what I want to call a raviolo. Just as some nomenclature. I have these three disks where I'm identifying points away from z equals 0. And of course, everything is constant in time. So I can imagine having two disks glued away from the origin, this sort of non-Hausdorff double-pointed origin space. And it looks something like a singular ravioli, also called a raviolo. But in any case, this moduli space MRav has two projection maps. I can either forget the data on the bottom disk, or I can forget the data on the top disk. And in some sense, MRav corresponds to, or is realizing a correspondence between these two moduli spaces. And when you're given such a correspondence, there's one natural thing you can do, which is a type of convolution. So I'm now over, but I'll be just 2 more minutes, I promise. The basic statement is that a geometric setup of this form implies that we have a natural product operation where I can take some homology class in MRAV, and I'll just call this the bottom disk rather than throwing all those extra bits. And this lands in the homology of the moduli space on the top disk. And the way this works is that some local operator, this thing that we have in the middle, is going to be some cohomology class in this Raviolo space. A state on the bottom disk is going to be some cohomology class in this homology of the bottom disk. And this is going to get mapped to, well, first, I'm going to pull back by this map pi. And then I'm going to take a wedge product with O. I can do this in MRAV. And then I'm going to push it forward along the map pi prime to land in the top disk. And so this should define an action of MRAV on the homology of M bottom and sending it to M top. And so the statement then is that these homology classes are going to be the morphisms in our category of line operators. When there is no line operator, Tudor and Justin and I guess Davide Gaiotto and Hyun Kim described this sort of action in a paper they wrote, oh, I don't know, ages ago. Vortices and Vermas is the name of the paper. Oh, I'm so sorry. Ichol Kim and Matt Bullymore. In our paper with Tudor and Justin and Mike Gerasi, we described this in more generality in this context of line operators. And of course, this isn't a particularly explicit construction. You have to be very powerful to do these convolution products. But next week, Tudor will be telling us about how to get this category in another way from vertex operator algebras. But there's yet another way to describe this category that I want to just highlight, which is much more geometric in a sense. And it's given by D modules on this space RK. You can kind of see this because I had to choose some Lagrangian, and Lagrangians sometimes have things to do with D modules. And we have to take some equivariance of these G modules with respect to this group of holomorphic loop group transformations. And so the claim is that this convolution product of the Raviolo moduli space and these vortex moduli spaces is a representation of this category of D modules. Okay, well, I'm definitely over now, but I only took 5 minutes. So I guess I should probably stop there.
Thank you. Are there any comments, questions? Justin?
Just to give you more time, can you explain more carefully what you mean by a representation?
Yeah, of course, I would love to. Thank you. So the basic statement is that, well, one categorical level below in like theory of algebra, what is a representation? Well, it's a map. Well, I choose a vector space, and I choose a map from my algebra A into endomorphisms of my vector space V. And in this context, we're just going to do that one categorical level above, representation. What this is going to correspond to, I have my category C, and a representation is going to be a functor from C to a vector space, or the category of vector spaces. In particular, for every object in C, one of our line operators, I guess I was calling them just L, I should have a vector space, V sub L, maybe I'll even call it H. And for every morphism, I'll call it O. That's a homomorphism from L to L prime. I should get a morphism in this vector space category. I.e., I should get some linear map from HL to HL prime. And that's exactly what we have here. For every local operator thing I can insert, I should be able to come up with a linear map from HL to HL prime, an entire analogy to what we have here, where we have some element sent to row of that element. One categorical level above looks something like this. Yes. The name of that functor. Oh yeah, sorry. Yes, of course. So in this case, our functor is labeled by that massive vacuum, and it is given by POM out of POM in the category C from our line into BV. I guess I then need to explain how BV is a D module. But yeah. I guess one other thing I should say is that this is really a derived category one has here, but I don't really want to say much about that.
We are just almost, so the time is almost over, but I can just maybe ask a very short question that maybe requires a longer answer, which is, so what does this have to do with this generalized defined Springer theory that you also advertised in your abstract?
Yeah, so the massive boundary conditions that I talk about over here are just one of a large class of choices you can make. In particular, we can actually have more interesting boundary conditions where at infinity, I don't approach some constant value, but have some more interesting profile to my gauge fields. So more generally, I can imagine that nu is some distinguished element in, for example, this cotangent bundle. And in the case where there's no line operator, Justin and Joel Kamnitzer and Alex Weeks describe how such a setup leads to a natural generalization of affine Springer theory. Affine Springer theory is an affine version of Springer theory, which is a geometric description of representations of groups by way of homologies of flag varieties. And so in this affine setting or generalized affine setting, these sorts of moduli spaces M that I have here, which is literally what you would have with nu being some more general element, are analogs of these flag varieties in the usual Springer fiber case. And this convolution product that we have here is a natural generalization of the Springer action on those homologies.
Okay, so let's thank Niklas again.
Oh, I should say, the more general setting with line operators in this generalized affine Springer theory was actually described by myself and Oscar Kivinen. And we do lots of cool things related to Homfli with Tudor and Justin and Lev Rozansky and Alexia Blumkov. So there's a very great story where this all fits into some highly non-trivial geometry. That's very exciting stuff. Just trying to plug the work. But before you leave, I think it would be a good idea to thank the organizers for this lovely workshop that we've all gotten to enjoy and for inviting us speakers to present our work. So thank you, Nuno and Sushmita. I look forward to the great talks next week. But I guess we're just done with the first week.
We have more next week, and and we already have some of the speakers for next week arriving. So yeah, so there's more to come. Thank you.